In this chapter, we will talk about alkyl halides, an important functional group in organic, and one of the reactions that the alkyl halide undergoes, which is the nucleophilic substitution reaction. Alkyl halides are water insoluble organics, meaning that they are not water soluble, no matter how many carbons they are attached to. They are only soluble in organic solvents. The halogen can be any of the halogens indicated here, and the hybridization of the R can be either an sp2 hybridization or it can be an sp3 hybridization. However, for our reaction, the nucleophilic substitution reaction, the reaction only goes whenever the hybridization of the R is an sp3 hybridization and not an sp2 hybridization. There are multiple types of alkyl halides, primary, secondary, and tertiary. So to look at the primary alkyl halide, you need to look at the carbon that is attached to the halogen and see how many carbons it is connected to. So if it is connected to one carbon, then in this case, it will be called primary alkyl halide. The hybridization here of this carbon is an sp3 hybrid carbon, which we need for the nucleophilic substitution reaction. If your alkyl halide is a secondary alkyl halide, then in this case, it needs to be connected to two carbons. And if it is a tertiary alkyl halide, then it's going to be connected to three carbons. Notice that I am highlighting the carbon that is attached to the halogen, and this is how I determine the type of the alkyl halide. Now, this carbon, as I said, it has to be an sp3 hybridization for the nucleophilic substitution to happen. With respect to the naming of alkyl halides, they can be named either by IUPAC or by a common name. If they are a short chain, less than 6 or 7 carbons, you can use the common name to name those. For the IUPAC name, you name the longest alkane chain, and then you name the halogen as a substituent, like bromo, chloro, so it's a halo substituent in there. If your halogen is on carbon number 1, you don't have to say 1 bromo, just name it as bromopropane. To name as a common, you start by naming your alkane chain first, and you name it as an alkyl group. So you end it in YL, and then you end the naming with a halogen, and the halogen ending is IDE. This is 6 carbon cycle, so I can also name it as a common name as well. If you have more than one substituent, then in this case, you would need to give your halogen the lowest number or the first substituent the lowest number possible. So this is why I'm going to number from this end over here, giving the iodine the lowest number possible and the methyl also the lowest number. And then name your substituents. Please make sure that there is a dash between the number and the name. If there are two numbers in there and two identical substituents, make sure that you put a comma in between. In addition to primary, secondary, and tertiary, alkyl halides can also be classified as allylic and benzylic. An allylic carbon is a carbon that is located on carbon number 3 of the double bond. So this is called an allylic carbon. Allylic carbons are known to be an sp3 hybridization and not an sp2 hybridization. So for these types of alkyl halides, the nucleophilic substitution reaction applies. So always whenever you want to determine where is your allylic alkyl halide, you number your double bonds, and if your halogen is placed on carbon number 3 of the double bond, then this is the allylic carbon, and the bromine on it is going to be the allylic bromine because it is on the allylic carbon. Also, if there are any hydrogens in there, here in this case, I do have two hydrogens. I have a hydrogen here. So I have a hydrogen here and I have a hydrogen here. So we're going to call these two hydrogens also allylic hydrogens. So anything that is present on the allylic carbon is called allylic, whether it is a hydrogen or a bromine. sp3 hybrid carbon. Now, allylic carbons, they come in types. They come as primary, as a secondary, and as a tertiary. Let's have an example in there. So let's say, for example, if I have something like this, okay? If I have something like this over here, and I want to determine what type of alkyl halide that is. So the first thing that I would need to do is to check my double bond and to check the position of the halogen that is connected to the double bond. So the halogen here is on carbon number 3 of the double bond. Now again here, I'm not gonna number for the sake of naming. I'm just gonna number to determine where the bromine is. Is it on carbon number 3 of the double bond? You can start numbering anywhere you want because you are not naming in this case. Here, the bromine is on carbon number 3 of the double bond. So this is called the allylic carbon. So this one over here is the allylic carbon. So as we mentioned, the allylic carbon is always an sp3 hybrid carbon in there. Now the type of this alkyl halide is going to be an allylic alkyl halide. But allylic alkyl halides, they are classified as primary, secondary, and tertiary. So you have to look at the carbon of the alkyl halide and see how many carbons it is connected to. So the alkyl halide is connected to 1, to 2, and to 3 carbons in this case. So this is going to be called a tertiary allylic alkyl halide. Okay, let's have another example. Something like this one over here. So this one is again an allylic alkyl halide because this is my double bond over here. And if I want a number, it's going to be 1, 2, and 3. So the alkyl halide is on carbon number 3. This is going to be my allylic sp3 carbon, or the allylic carbon is connected to 2 carbons. It's connected to a carbon here and a carbon there. So this is called a secondary allylic alkyl halide. For example, over here, this is an example of a primary allylic alkyl halide because my double bond is here. And if I want a number, that's going to be 1, 2, and 3. So this is going to be my allylic sp3 hybrid carbon. And that allylic carbon is connected to just to 1 carbon. So this is your allylic carbon over here. And the allylic carbon is connected to just 1 carbon. So this is going to be a primary allylic alkyl halide. So these are the 3 cases of allylic alkyl halides. They can be classified as primary, secondary, or tertiary. To locate those again, you locate where is your allylic carbon in there and see how many carbons it is connected to. The allylic carbon has to have the halogen attached to it to be called an allylic alkyl halide, or else it will be just an allylic carbon without the alkyl halide. The other types of alkyl halides, for example, over here, the primary, secondary, and tertiary. So see, this one has no double bond that is close to the bromine. Notice that the double bond is adjacent to the allylic carbon. So there is no double bond in here. So this is a regular secondary, or it's a regular primary alkyl halide. This is my alkyl halide in there. And the carbon is connected to 1 carbon. This is my sp3 hybrid carbon here, and it's connected to 1 carbon. So this one is a primary alkyl halide. Now notice for this example here, the double bond is far away from the carbon that is connected to the alkyl halide. Because if I start numbering from here, this is going to be 1, 2, 3, and 4. So this carbon here is not an allylic carbon. So this one is not an allylic carbon because it is not on position number 3 of the double bond. It is an sp3 hybrid carbon though, so substitution, nucleophilic substitution happens in here. But here, if I want to classify this alkyl halide, it's going to be a regular secondary alkyl halide because it is connected to two carbons. So this one is going to be a secondary alkyl halide. This one over here is a regular tertiary alkyl halide. So this is my alkyl halide, and that alkyl halide is connected to carbons 1, 2, and 3. So it's a regular tertiary alkyl halide in there. Here, my alkyl halide is far away from the double bond. If I start numbering, this is going to be 1, 2, 3, 4, and 5. It's very far away. So it's not on the allylic position, but it is an sp3 hybrid carbon, so nucleophilic substitution undergoes. The type of the alkyl halide here, since it is connected to two carbons, then this is called a secondary alkyl halide. Another type of alkyl halides are benzylic alkyl halides. Benzylic alkyl halides, they are alkyl halides that are connected to a benzylic carbon. And the benzylic carbon is a carbon that is directly connected to the benzene. To name these compounds, you use the word benzylic with the common name. So here, benzylic is a benzene connected to the carbon. So when I say benzylic, I mean by that it's going to be all this portion in here. The benzylic carbon included with the benzene. This whole thing is named benzylic. So this is going to be benzylic chloride, benzylic bromide, depending on the halogen that is connected to. When I want to name it as an IUPAC, then in this case, the name is going to be ended with benzene. And here, it's one carbon, so it's a methyl group. So it's going to be chloro, it's a methyl, and all of those, they are off the cycle of the benzene. Remember at the end, whenever you name IUPAC, your longest carbon cycle or carbon chain has to be at the end. This is why I'm ending it with benzene. As we did for allylic carbons, we're going to do exactly the same for benzylic carbons. So benzylic alkyl halides, they are classified into primary, secondary, and tertiary. Let's have some examples in there. We'll be working with these 4 examples. So again, you need to have a benzene to be named a benzylic. So if you have like a cycle that has just one double bond, this is not a benzene. So you cannot name it as a benzylic. So my cycle that is a benzene is this one. So I need to have a cycle that is a benzene. So I'm going to highlight all of those benzenes in there. And then you're going to look at the carbon that is directly connected to the benzene. So this is the carbon that is directly connected to the benzene over here. So this means that this one is not going to be a benzylic because the bromine is not connected to the benzylic carbon. This is the benzylic carbon over here. So this one is the benzylic, and the bromine is not connected to that. So I'm going to name this as a regular alkyl halide. You're going to highlight the carbon that is connected to the bromine and see how many carbons it is connected to. So it's connected to 2 carbons. So this guy is going to be a secondary regular alkyl halide. As for these examples there, the bromine is directly on the benzylic carbon. So that benzylic carbon, if it is connected to 3 groups, so 3 carbons, so you have a carbon here, and a carbon here, and this is going to be your benzylic carbon that is connected to the halogen, then in this case, this is called a tertiary alkyl halide or a tertiary benzylic alkyl halide. So this is going to be a tertiary benzylic alkyl halide, and the halogen is a bromine, so you can call it a tertiary benzylic alkyl bromide. This one is going to be a secondary benzylic alkyl halide or alkyl bromide, and this one over here This is the carbon, the benzylic carbon that is connected to the bromine, and it's connected to one carbon. So it's going to be a primary benzylic alkyl bromide. Nucleophilic substitution reactions, they involve the breaking of the sigma bond. The sigma bond has to be a bond between the halogen and the sp3 hybrid carbon. Normally, sigma bonds, compared to double bonds, they are longer bonds and easier to break. So let's say, for example, if I have a carbon that is connected to a halogen and that carbon is directly attached to a double bond, then in this case, this carbon over here is going to be an sp2 hybrid carbon. So why we say that nucleophilic substitution reactions, they only happen with sp3 carbon, hybrid carbon, and not an sp2. The reason is the length of the sigma bond. We know that the sigma bond that is directly attached to the sp2 hybrid carbon is shorter than the sigma bond that is attached to the sp3 hybrid carbon. Also, the sigma bond that is attached to the sp3 hybrid carbon is a longer bond and it's a weaker bond. So this bond over here is easier to break than this bond. If you have the halogen directly attached to the benzene, not on the benzylic carbon, they are directly attached to the benzene, then in this case, this is an sp2 hybrid carbon, so the reaction will not work. So always to check if the reaction works or not, you need your halogen to be attached to an sp3 hybrid carbon and not an sp2 hybrid carbon, because sp3 hybrid carbons, they do have longer sigma bonds and their sigma bonds are easier to break because the sp3 is less electronegative than the sp2. These structures, they do also have a name, like the allylic, but they differ from the allylic because there is no sp3 hybrid carbon in between the double bond and the halogen. The halogen is directly attached to the double bond. So if your halogen here is directly attached to the double bond, this is carbon 1, this is carbon number 2, so it's on carbon number 2 of the alkene, then we're going to name this structure a vinyl. And this carbon here will be called a vinylic carbon. If there's any hydrogens on this carbon, so here I do have two hydrogens as well. Okay, all of these two carbons are called vinylic carbons, both of them actually. They are called vinylic carbons, and the hydrogens that are attached to the carbons are called vinylic hydrogens. If you have a halogen that is attached to the vinylic carbon, then we're going to call it a vinyl, and then you name that halogen. Um, If you have a halogen that is attached to the benzene, you cannot name it benzylic now because benzylic, it has a carbon between the benzene and the halogen. So this is called simply an aryl halide, or it's called a phenyl halide. So we call it a phenyl halide. And there's a difference between a phenyl and a benzyl. So this is a phenyl halide. A benzyl halide is whenever you have a benzylic carbon, and on that benzylic carbon you have a halogen. So this is called a benzylic halide. This is called a phenyl. Phenyl is simply a benzene, and you have your halogen directly off the benzene. So it's going to be a phenyl halide in this case. Okay, let's have an example. Now, the vinylic is not like the allylic. So the vinylic halides, they are not classified as primary, secondary, and tertiary. Same thing for the aryl halide or the phenyl halide. There's no classification for them. It's just the halogen attached to the sp2 hybrid carbon. And if the sp2 hybrid carbon is the double bond, you call it vinylic. If it is a benzene, you call it a phenyl or an allyl. Let's have an example in here. So something like that. See the double bond in there, the bromine is directly attached to the sp2 hybrid carbon. Then in this case, this is going to be called a vinyl bromide. Okay, so the type here is going to be called a vinyl bromide. Alkyl halides are slightly polar organic compounds. After all, alkyl halides, they are not water soluble, they are soluble in organic solvents only. The only type of intermolecular forces in alkyl halides is the dipole-dipole interaction, and the only polar bond in the alkyl halide is the carbon that is attached to the halogen. This is the only polar bond. The reason why it's polar because of the difference in electronegativity between the carbon and the halogen. Look at the electronic map in here, it just shows how the electron flows. The red region shows that this atom is electron rich, and the blue region shows that the carbon is electron poor. The reason for that is because chlorine is more electronegative than the carbon, so it's going to pull electrons away from the carbon, making itself electron rich and the carbon electron poor. To represent the carbon being an electron poor, you put a partial positive charge. And now the carbon will be our electrophile. And this is where the reaction is going to be on this carbon because this carbon is in desperate need of electrons. There are multiple ways to write a general reaction. In all of the ways, the reactants, the products, the reagents are there, but we arrange them differently or we write them in different positions. So you start always with your reactant, and you end up with your product in there. Okay. Now, reactants always react with reagents, and the reagent can be above the arrow. So this is the reagent, or it can be before the arrow. So this is going to be my reagent. Reagent is whatever the reactant is reacting with. Okay. And then you have the reaction conditions and the solvent. Now, normally the solvent is placed either above the arrow. So this one over here is the solvent. And the role for the solvent is to dissolve the reactants with the reagent. If your solvent has a hydrogen, then it will have a role at the end, which we call protonation, meaning that it will donate a hydrogen to get the neutral product. But if it doesn't have a hydrogen, then it's going to just act as a solvent to make the reagent and the reactants miscible with each other. Solvent can be in two positions, either above the arrow like that or underneath the arrow. So here I do have my solvent. And then you have reaction conditions. The reaction conditions can either be underneath the arrow, like here. So both of these, they show reaction conditions underneath the arrow. Okay. Or they can be next to the solvent. So instead of writing them underneath the arrow, I can simply put a comma in there and put the reaction conditions, which is light or heat. So it depends where do you want to position them, and all the positions are right, either underneath the arrow or after the solvent. This is a reaction that is one step reaction. So in one step reaction, you have a reactant, you have one reagent in there, and then you have your reaction conditions, and then the solvent, and then you have your product. There are reactions that are more than one step. And if this is the case, then every step should have its own reagent, and every step should be labeled by the number of the step. So here, if I have two numbers, then I know that the reaction is two steps in there. So the first step, I am reacting my reactants, which is the ketone in this case. So this is my reactant. I am reacting it with the reagent. And next to the reagent here, I do have my solvent. Solvents are a must because reagents, most of the time, they are not miscible with the reactants. So you want to dissolve the reagent with the reactant. So you want to put a solvent in there. The solvent here is two ethyl groups that are on both ends of the oxygen. This is an ether, and we call it a diethyl ether solvent. So that is going to be my first step. The product of the first step is not shown in here. This is the final product of the two steps. Now, in the second step, I'm using water. In the second step, I have water, and water here is going to be my second reagent. So this one is going to be my second reagent. And after I'm done from the water in the second step, I am getting my final product, which is the tertiary alcohol.